Now, we want to solve Poisson's equation in this coordinate system. For that, we can go to the definition of the Laplacian in terms of the scalar factors of a coordinate system. And the scale factors of the elliptic coordinate system are given by HU and H nu. They are the same, given by this expression. And phi, the direction of symmetry, is given by this other expression. Of course, I'm not going to compute this by hand. Let's use SymPy. Let's load the symbols and the function phi for the potential. Let's write the scale factors. That's the first scale factor, H1. H2 is equal to H1. And H3 is given by this other expression. We define now du, which is the first term, dv and dphi, the second and the third term, and the Laplacian. Let's see the expression. Well, looks horrible. But luckily, we're interested in potentials that depend only on u, because u is what has the shape of the ellipsoids. So we are going to discard potentials that depend on nu, or they depend on phi, the three-dimensional coordinate of symmetry. Now, for potentials of this class, the Laplace equation reduces to this form, which is considerably simpler. Now, there are two solutions here. One is if phi is equal constant, so this first derivative cancels. And the second one is if we make the argument that is between parentheses cancel. That is if d phi du is equal to 1 over the hyperbolic cosine of u. That means up to a constant, phi prime should be the arcsecond, the hyperbolic arcsecond of u. If you integrate this phi prime then in u, we find the potential. So that's the potential in the end, is the arcsine of the hyperbolic second of u plus an integration constant b. Now, this doesn't look too transparent, but we can tell some things. First, that the potential should yield the spherical potential at large radius. We can see that because at large u, these confocal ellipses become more and more circular. So at very large u, you expect the potential to be spherically symmetric. Now let's see the definition of u here. So this is the definition of RZ in terms of u. Let's see the R. If we ignore here the sine nu, say that we are in the z-axis, so that sine nu is equal 1. And then we have that the hyperbolic cosine of u is r over f. So the hyperbolic secant is f over r. So a large r, the potential will scale like the arcsine of f over r plus b. One thing that we immediately see is that as if r goes to infinity, for the potential to be 0, then this quantity b here has to be 0. Another thing is that for large r, we have here this quantity f over r being very small, and the arcsine of the quantity becomes the quantity itself. So for the limit of r being much bigger than the focal distance, this is the potential that we have. So we need to cancel b. Now, the spherically symmetric potential is minus gm over r. To make these two equations match, we need to have a being equal to, a is equal to g times mass over f, with delta m being the mass of the homoeoid, then indeed the potential is equal to that of a shell of mass delta m. We found then what the integration constants are. A is equal to gm over f and b is equal to 0. So we take these constants to the general potential. Again, this is the general potential. And the other solution was the potential being constant. So we can write both solutions in a piecewise function, writing it in this way. For u bigger than u naught, you have the solution that depends on u. And for u inside u naught, you have a constant. The potential is continuous. So this is the constant, and the value of this potential continues to be this inside of the shell labeled by u naught. Now this is the solution for Laplace equation, which is nabla square phi is equal to 0. That describes the potential everywhere except where you have mass. Now this shell is infinitesimally thin. So that means that this is describing the potential everywhere except the u naught. So this describes the potential of a shell that is located at the position u equal to u naught, which is the shell here with the black line. Now we can simplify it a little further. If we can write the potential in terms of the eccentricity, noting that F is the focal length equal to the semi-major axis times the eccentricity. Another simplification that we can make is that U0 is related to the eccentricity of the shell. We can see here, right? Each of the confocal ellipses has its own eccentricity. So each value of U is related to a particular eccentricity, which you can also see here from this equation. So we can convert U into a value for eccentricity. We can do that by considering the semi-major axis, A equal to F times the hyperbolic cosine of U0, and the semi-minor axis is equal to F times the hyperbolic side of U0. If you divide one by the other, you have the hyperbolic tangent of U. Now, if you use the trigonometric identity between the hyperbolic tangent and the hyperbolic secant, the one plus the other is equal to 1, then I have this expression, 1 minus c squared over a squared, which is the eccentricity. So this is a simple expression for the homoeoid potential, g times the mass over semi-major axis times eccentricity, times the arcsine of the eccentricity of the homoeoid for the potential inside, so that's a constant. Inside, you have only g times the mass over a, and outside of the homoeoid, you have a dependency on u. But we already found the mass of the homoeoid. With the substitution, then, we have this expression for the potential of the homoeoid. So let's look at the potentials. There we go. This is the potential for an homoeoid of eccentricity 0.9. So it's bound here by this. So that's the shell here where the homoeoid is, the first contour. Inside, the potential is constant, and outside, as you see, the potential is becoming more circular. And this is the potential for an homoeoid of eccentricity 0.5. Again, here is where the homoeoid lies. Inside it, the potential is constant, and outside, again, you have this concentric ellipses until it becomes more and more circular. What is shown here is the potential as a function of u. The blue line is for eccentricity 0.9. The red one is for eccentricity 0.5, and the dotted line is the circular potential that matches at infinity. So that's the potential of a spherically symmetric shell located at the same position. You see here that the shell indeed matches most of the distribution. For eccentricity 0.5, the spherical shell is in fact a very good approximation. For 0.9, it is a good approximation, but less so up to a certain point, as expected for a very flattened distribution. So two theorems are true for homoeoid mass shells. The first one is that the exterior isopotential surfaces of an homoeoid are ellipsoids that are confocal with the shell. That's what we see here. We have these confocal ellipses that are giving the potential outside of the homoeoid. And the second one is that inside the homoeoid, the potential is constant. Again, we see here in these plots. This is actually Newton's third theorem. So we're done with the homoeoid potential. With these equations, the potential of any axisymmetric ellipsoid can be found. And the idea is simply to integrate over all shells in the same way that we did for the spherical symmetric case. But instead of integrating over spherical shells, we're now integrating over oblate shells, the homoeoids.